All right, so when I went through and I solved here for x, x is equal to 1.1 times 10 to the minus 1, 2, 3, 4, 5. 10 to the negative fifth molar, okay? So if we're going to solve for the pH then, right, we've got x here is 1.1 times 10 to the minus fifth molar. That is going to be our OH minus concentration. So our OH minus concentration is going to equal 1.1 times 10 to the minus fifth. So our pOH is going to be the negative log of that. So negative log, where's my log button? There we are. Of 1.1 times 10 to the minus fifth. So our pOH is 4.93. That would mean our pH, 14 minus that, would be 9.07. Okay? Now this makes sense, of course, right? We are adding NaF. That means that really we're adding F minus, which is a base. So if we're going to add a base into our water, right, we are going to make our water be basic, right? Our pH should be greater than 7, okay? So that's good. So every time, right, we want to check and make sure that our answer makes sense, okay? All right, so let's go through again. Let's look at our Kb, pKb, all of that with a different reaction. Right now we have a base with water. Right, same idea as we had over here. So we are going to have a Kb, right, rather than the Ka. Kb is going to equal concentration of NH4 plus times the concentration of OH minus divided by concentration of NH3. Okay? Same as before, right? We would be able to have pKb. pKb is going to be negative log of the Kb value. Okay? So we can do this with acids or bases, right? We use either Ka or Kb to signify that is an acid or a base, right? We can go ahead and use these relationships with our equilibrium expressions and our equilibrium reactions, okay? We can also do a percent ionization calculation, okay? So I've written out a question here, right? A weak acid is in solution. pKa is 4.994. The pH is 4.523. What is the percent ionization, right? So if we notice here, right, we've got an acid, so let's write out our Ka expression. That's going to be A minus times H plus or H3O plus. I'm going to do H3O plus here because we're in water in a solution, divided by HA concentration. Okay? So we go there, and now we say, well, we know pH. That means that I can calculate my H plus concentration. So pH is 4.523. I want to convert that to my H plus concentration. So I'm going to do 10 to the negative 4.523. My number here should be somewhere, I think, between 4 and 5. Or 10 to the negative fourth or fifth. So 10 to the negative 4.523. Turns out we have our H plus concentration, or H3O plus concentration, is equal to 2.9, and I'll do 2.99 times 10 to the minus fifth. Or really, I can do 3.0. 3.00. times 10 to the minus fifth. Okay? So now we know that value. We also know the pKa. So if I know the pKa, I can calculate my Ka. So Ka is going to be equal to 10 to the minus pKa, which is 10 to the minus 4.994. So we're going to again have another 10 to the negative fifth number. 10 to the negative 4.994 is equal to 1.0139 times 10 to the negative fifth. Okay? So now the last piece here is that if we have an acid, right, HA, it's going to split up into A minus and HA. Well, I know my, and H plus. I know my H plus concentration. It is a 1-to-1 relationship between my H plus and my A minus. So now I know 1.0139 times 10 to the negative fifth is equal to A minus. That would be the same as my H plus. So 3.00 times 10 to the negative fifth times 3.00 times 10 to the negative fifth divided by my H plus, or HA concentration. I can solve for HA concentration. HA equals 8.88 times 10 to the negative fifth. So now then I have my A minus over HA. I can do a percentage. So 3.00 times 10 to the negative fifth over 8.88 times 10 to the negative fifth. That equals 33.8% ionized. Okay? So that's just kind of some extra little math tricks that we can do as well. Okay? Okay, we've got a couple more sections here. Let's talk about strong versus weak acids, okay? What if we have a strong acid and a weak acid in there, right? Here's a hint. Strong overcomes weak. Strong overcomes the weak. So if we have a strong acid and a weak base, the strong acid is going to win, okay? If we have a strong acid and a strong base, really the reaction that we have is H plus and OH minus goes to H2O, right? The pH is really just determined by that excess reactant. If we've got an excess reactant, we should be able to calculate, say how much excess we have, and then that excess is going to tell us the OH minus concentration, or it's going to tell us the H plus concentration. We can go ahead and solve for pH, etc. Okay? So strong and strong is the easy piece here, all right? If we have a strong and a weak, again, the strong overcomes the weak, okay? So if we have a strong acid, a weak base. So this would be strong acid, weak base. Strong is going to overcome the weak. We are kind of mostly going to be over on this side here, okay? So, but if we have an excess acid, right, strong acid, then we're going to get pushed over that way. We'll be able to use how much excess acid we have, okay? But if we have a strong acid, weak base, and we have the weak base in excess, right, we're pretty much going to use all of that H3O plus, but then we're going to get this equilibrium that we are going to go back and forth between, right, until we get to that equilibrium. That is when we're going to use the Henderson-Hasselbalch equation. That Henderson-Hasselbalch equation we are going to talk about here later at the end, okay? But if we have a weak acid, strong base, again, strong overcomes the weak, we're going to shift, we're going to be forced that way, okay? If we have a weak acid and a weak base, then our overall reaction is more like this, okay? And then things can get complicated, okay? So let's talk about graphical representations of our strong acids and bases. Well, that would be titrations, okay? We didn't get to do a titration in last year. Maybe we did, I don't know. But, right, titrations are really just a relationship where we plot pH versus some amount of titrant, okay? So we're going to add something And we're going to try and calculate then what the actual pH of our initial source is, okay? So we would have some sort of container. We'll add in to that container, and we'll measure the pH, right? So in that container, we've got something of an unknown concentration. And then up here in what's called a burette, we're going to have a known concentration, okay? So we're going to add that known concentration in, and we'll be able to measure that pH, and then we'll be able to see what happens to the pH, okay? So if we have a strong acid being titrated with a strong base, right? We've got a strong acid to start, so our pH would be low, right? So we start low, and then at a certain point, we're going to jump up because we're going to start having excess base, okay? So right here in the middle, right at that most vertical point, that would be our equivalence point, okay? So the equivalence point, if we have a strong acid and a strong base, is right at pH 7, okay? Strong acid and strong base, that equivalence point is at pH of 7. That is where, right, the equivalence point is where we have added the same amount, right, the same moles of base as we have started with acid. So because we have a strong acid and strong base, right, we are just forming H2O, okay? But if we have so this is strong acid, strong base, right? If we have a strong acid that is being titrated by if we have a weak acid being titrated with a strong base, we're going to see that we've got this long spot here where our pH doesn't change very much, even though we're adding lots of base. And then we'll get past that point, we'll again jump up, okay? So here now, our most vertical point is actually going to be up above 7, our pH at that equivalence point. Maybe it's up at pH of 9, okay? So when we have a weak acid and a strong base, the equivalence point is going to be above pH of 7, okay? We're going to come back in a second here because I'm running out of time.